Hello everyone, this is Harry Gill. In this video, we are going to look into a demo of performance test in between a Spring Boot web application and a Spring Boot Webflux application. Before we dive into the demo, just wanted to go over the main difference between the web and the Webflux. So on this screen, we will discuss the web application. So a typical Spring Boot web application will have these components. So we would have Apache Tomcat, controller, service, repo, and a database. Now, whenever a client sends a request, it goes to, first of all, to the web server, which we have in this case is a Apache Tomcat. Now, the main thing here to note is that whenever the request comes in, Apache Tomcat will start a thread for that request. When the thread is started, the control is passed to the controller, and then it goes to the service layer repository, and then we talk to database. And in this whole flow, the main important thing is the thread that we created in Tomcat Apache is still live. Now, database might take some time querying the database. Let's say it takes 10 seconds, and after 10 seconds, it decides to return the response. And it goes to repo, goes up the service layer, and then to the controller. And then finally, the response goes to the Tomcat Apache. And now Apache returns the response to the client and it kills the thread. Now let's consider this scenario where there are three clients. So we get three requests at the exact same time. Apache will create three different threads, one for each client. And then the flow goes as we just discussed for each of these clients. Now let's move on to the Webflux application. So the structure of the whole application is actually very similar. The main difference is that instead of using the Tomcat Apache, the Spring Boot Webflux application uses the Reactor Netty. And Reactor Netty is based on an event-driven architecture. Event-driven is a programming concept that we will discuss into a different video, but that's the concept that's used in Webflux. But I'll give you a very high-level idea. So in this case, when the request comes in, it goes to the Reactor Netty. Reactor Netty will start a thread, just like Tomcat did, and then it passes the control to the controller. Now the main difference is once it's done, it doesn't keep that thread alive. It will actually remove that thread, and now that thread that got released can serve the next traffic. In our example, the control is now with the controller. Controller calls the service. Again, controller doesn't keep the thread alive, and the data keeps flowing down the layer and to the DB. Now, database might take long time to return back. The main thing to note here is that we are not tying a thread at this stage. So we don't have any live thread in our example. Whenever data is ready, it will push the data back to repository, which will get pushed back to service layer and so on. The control is exactly same. It's just that now we didn't hold the thread. Reactor Netty will now respond it back to the client. Now let's say instead of having one request, we get three different clients. The flow is exactly same. Reactor Netty will start three threads and then pass on the control to the controller and so on. Again, Reactor Netty will not keep the thread alive. What that means is now Spring Boot Webflux application now can take more parallel requests. And if there is some time taken in the background, then it doesn't need to keep the threads alive. Now let's jump into the IntelliJ and look at the example. So what we see now here is the Spring Boot application. So this is the web application. I have written it in Kotlin, but you could use it Java as well. It doesn't make much difference. I'll go through the application. It's a very simple application. I will also provide the link of the code in the description. So we have exposed an endpoint called hello, and that calls the service. And within the service, there is a method called say hello. In here, I have put a sleep of 1 second. And then all I did is I returned a string from here. Very simple application. So the reason I have added a sleep is to simulate a delay. So whenever we interact with the database or when we do heavy computation, there will be some delay. So the sleep is put just to pretend that delay. Now let's have a look at the Springboot Webflux application. So the main difference on why it's a Springboot Web and Springboot Web application is through the dependencies. For Springboot, we use Springboot Starter Web, but for the Webflux application, we will use Springboot Starter Webflux. So we are in the controller. I have done exact same thing, exposed an endpoint hello, and that goes to service within the service. So this mono is a reactive programming concept. Reactive programming we'll probably discuss in a different video, but for now, just think of it as, in this particular case, what I'm doing is I'm creating a string and I am delaying that for 1 second. It is to simulate that 1 second delay, how we have done in the Spring Boot application. And after 1 second, it's going to return the hello word with the local time when I run it. So as you see, the code for both are very, very similar. Before we jump into the demo, one quick thing I want to highlight is that the non-blocking service, which is the Webflux one, is running on port 8091, and the Spring Boot web application is running on port 8090. And I have also integrated Prometheus and Grafana in this setup so that we can have a look at the graph as well. Now let's jump into the terminal and start the demo. Go ahead and get the code link from the description, clone the code onto your local. So this code will have two different microservices. So we have a blocking service microservice, and this particular is the Spring Boot web application. And we have another service called non-blocking service. This is the Spring Boot Webflux application. If you want to have a look at the code in IntelliJ, you can open these two different projects independently in two different windows. Apart from these, I have Prometheus and Grafana configuration, and I have used Docker Compose to do the whole setup. So as soon as you download, the very first thing you will do is let's build both the services. So cd blocking service, Gradle, build. So the build is now complete. Now let's go to the non-blocking service and build this service. So remember, this is a very important step because the Docker Compose will not build it. It will only create the Docker image and start the application. Now go back one directory and run Docker Compose up -- build. And now it is going to create the Docker image. It's doing for blocking service. And it did for non-blocking service as well. Now it's downloading the Prometheus Docker image. And now it's pulling the Grafana image. And now it's starting the applications. So as you see here in the log, so we have blocking service and a non-blocking service. And now both the application has been started. Now before we start doing the performance test, let's just hit curl command http. So 8090 is where my one application is running. So this is the Spring Boot web application. So it worked fine. And now let me hit 8091. So this is the Webflux one. Cool. So both the services are working fine. Now let's head into the browser and let's configure Grafana to get the metrics. Let's go to the URL localhost 3000. This is where the Grafana is set to run. Now the first thing we need to do is create a data source. You can click here or you can go in the menu. So add data source. In our case, it's Prometheus. And we'll add the URL. Since we are running Prometheus in the Docker image, we will have to get the IP address of the Docker image. So let's head back to the terminal and get the IP address. So we will use the docker inspect command. So I have mentioned the command in the README of the project. So that's our IP address. Let's head back into the browser. HTTP, then the IP address and colon 9090. So that's where I have configured Prometheus to run. Let's go to the end, save and test, and you should see this successful now. Let's go to build a dashboard, and now I'm going to build two different graphs. Add visualization, select the data store, and in the select matrix type Tomcat threads, current threads. Run the query. So you will see a graph here. Let's change the title as Tomcat threads and let's save it. Let's name the dashboard. Hit save. I'm also going to add another graph. And in this case, in the metrics, select HTTP _ server request seconds count. And in the select label, select for URI and let's select hello. This is the endpoint that we expose from both the microservices. Let's hit run query. Let's name it as requests per second and hit save. Let's go to our dashboard. And I'm going to bring both terminal and Grafana on the same window. Let's do a view on the Tomcat threads. We don't want last 6 hours. Let's probably do last 15 minutes. So what this graph is showing is the number of active threads in Tomcat server. Remember, Tomcat is part of the Springboot web application. So in my setup, Tomcat has decided to initialize 10 threads. Now I'm going to hit some concurrent requests to my web application. And for that, I am using a tool called Siege. I did use Apache Bench, but I was facing some problem on my local. And then I installed Siege and it has been working perfectly. So Siege is a performance test tool where we can send multiple requests to a server. You don't have to use Siege. If you're comfortable with any other tool, feel free to use that. I have just learned and used Siege. It has been working really well. In the case of Siege, we need to provide two different parameters. One is -c, and we have to give a number. Let's say 10, and then we have to -r 10, and then a URL. What I'm saying here is that I need to simulate that I have 10 concurrent users and each of the user is hitting 10 requests. So in total, this tool will send 100 requests to my application. So let's hit enter. In the Grafana, I'm going to set an auto refresh and let's do a refresh here. So we see a jump here. And the reason of this jump is that originally when Tomcat was idle, it had 10 active threads. As soon as I sent 10 requests to Tomcat, all the threads got used up, but Tomcat had more thread in its pool. So it activated them just to keep some buffer for the more requests. So in my case, it decided to bring up 14 threads. So I had 10 users, but Tomcat has 4 threads that can serve 4 more clients. And now I'm going back and I'll update this command and change it to 20. So now I have 20 users and each of the user is hitting 10 requests. So these users are all concurrent users. So in this case, we are going to hit 200 requests and get 200 responses. So I'm going to start the test now. So you see in the graph here, Tomcat has now increased the thread to 20. So previously they were 10, we hit 10 users came in, it raised to 14. Now 20 users came in, it raised it to 20. In the tools output, make a note of elapsed time, which is 10 seconds, which means it took total of 10 seconds to serve the requests. Now this is where things will get interesting. So I'm going to change my command and now I'm going to generate an load of 40 users and each user will send 10 requests. So all these 40 users are concurrent users. So I begin the test. All right, so the test has completed. So we have sent total of 400, which is expected. Now the elapsed time, as you see, is 20 seconds. Previously, when we had 20 users, the elapsed time was only 10 seconds, but now it has doubled. The reason why it doubled is because let's go back into the IntelliJ. In my current configuration, I have set up that my Tomcat can have at max of 20 threads only. So now what has happened here is, so due to this configuration, the max thread 20, Tomcat cannot go over 20 because I have asked or configured it in that way. Now, when I got a request from the 40 different clients, Tomcat could only serve first 20 requests. The other 20 were still waiting because there were no threads to serve the other 20 clients. The first 20 were served in around 10 seconds because each client is sending 10 requests and we have 1 second delay. So first batch got served in 10 seconds and the second batch got served in around 10 seconds. That is why we have got total of elapsed time of 20 seconds. Now checking the response time. So response time is still pretty good. Like average response time is like 1.97, which is good, not an issue. And the transaction rate is 19.80, which is close to 20. And the reason for this is because there are max of 20 threads and we have given 1 second of delay. Tomcat cannot process more than 20 requests per second as per our given configuration. So by default, like if I do not provide this configuration, by default, the total number of threads that Tomcat will have is 200. So what I'm going to do is I'm going to delete that configuration, which I have overridden, and I'm going to rebuild the application and restart everything. So let's move back here. So I'm hitting Control C. So let's first do the build because we have just changed the configuration. So we need to do the build and make note that I'm doing it in the blocking service because that's the service I have changed. So now let's bring our stack up again. So Docker compose up build. Okay, both of our applications are now up. Now let's hit the same request with 40 concurrent users. And notice that no matter how many users we increase, the thread count was still sitting at 20. It never went up. Now, because we have changed the configuration, now max thread is 200. So in this case, because there were 40 different users, so Tomcat has decided to start or make active 45 threads. So 40 of them were serving my requests and 5 were still ideal to have more clients. And in this case, the interesting bit here is elapsed time. So we came back to 10 seconds. So all our clients were served within 10 seconds. And the response time that we got was 1.07 second, which is expected. Transaction rate is 37.04 transactions per second because there were 40 different clients. That's why the transaction rate is closer to 40. So now hopefully your concept of threading is a bit clear from the Tomcat perspective. Like the whole aim of this demo was to show you the threads perspective. Like how does the threads count increase when the concurrency increases? Now let's jump into the actual performance test. What I'm going to do is I'm going to jump into the Google Sheet and create a table, and I'll note down some profiles, and we will run the test for both Springboot Web Application and Springboot Webflux application. So here is the table which we will use to record the performance on how two different apps perform. So we have Spring Web Application, which we will record the data here, and the Webflux, which we will record the data in these 3 columns. The data we are collecting is how much total time did it take to serve our customers. The other is average time per request in seconds. And the third matrix is throughput, which is number of transactions per second. So whenever we measure the performance, so average response time and throughput are the main metrics that we need, and we need to get high throughput and low average time as much as possible. So similarly, these 3 matrices will be recorded for the Webflux application as well. I'm going to run 4 different tests. In this case, we will have 200 concurrent users each user is hitting 10 requests. And the second test we will run is 400 concurrent users, and then 600 concurrent users, and finally 1000 concurrent users. For simplicity and not to change too many variables, so I have kept the number of requests per user constant. Now let's jump into the terminal and start the tests. Now first, I'm going to hit the service that's running on 8090, which is the Springboot Web Application. So I have 200 users that are requesting, and each user has 10 different requests. So let's start the test. So the test has finished. Now let's do the recording of the data. So elapsed time is 10 seconds, 98 milliseconds. So let's go to our sheet. So 10.98, let's just have 11. And the average response time is 1.06. So let's just have rounded to 1 second. And transaction rate is 182.15. So let's just mention 182. Now the same test will run, but for Webflux application. All right, so the test has completed. So we have hit 2000 requests. So the elapsed time is 10.69 seconds. So let's just put 11 to round it up. Response time is 1.04. So let's just have 1 second, and throughput is 187. So 187. So now if we compare the 2 results, you will notice that they're pretty much same. So we got all the customers got served in 11 seconds for Spring Web, and also 11 seconds for Webflux. Average response time was 1 second, and this is the delay we have put in the app. Similarly for Webflux, its average response time is 1 second, and throughput is 182 and 187. It's very slight difference. Now in the subsequent test, now is where we will start seeing a lot difference. The reason why both the results are same is we have 200 concurrent users, and as I have mentioned, the Tomcat server has 200 threads. So all the customers were being served in parallel. Now let's run the second test with 400 users. So I'm going to change the port to 8090, and let's also change to 400 concurrent users. Start the test. All right, so the test has completed. So we have hit the 4000 requests. So the elapsed time is 20 seconds. So let's make a note here. So 20 seconds. Let's see the average time. So it's about 1.98. So let's put 2 seconds, and 194 is the throughput. 194. Now let's run the same test for Webflux application. All right, so the test has completed now. We have hit the 4000 requests, and the elapsed time is 12.25 seconds. So let's mention here 12.25. The average response time is 1.18. So 1.18. Let's mention the decimals as well for these. And the transaction rate is 326. So 326. Now, for this test, there is a huge difference. The huge difference is, first of all, it took 20 seconds for Spring Web application to serve our 400 customers. The average response time for all the 4000 requests was 2 seconds. However, it took only 12 seconds for Webflux application to serve 400 customers, and the average response time was 1.18. So which means on average, our Webflux application has responded way faster than the Spring Web application. And the throughput is pretty high. In this case, we have 194, but we got 326 in case of the Webflux. So high throughput, low average time. So this test is, these results are better. So let me mark it in green. Now let's run the third test for 600 users. So we will hit 8090. And now we have 600 concurrent users. All right, so the test has completed. We have hit 6000, and total elapsed time is 30 seconds. So let's make that entry. Now average response time is 2.93. So let's do 3 seconds. And transaction rate is 195. Now let's run the same test for the Webflux application. All right, so the test is now complete. We have hit 6000 requests. So the total elapsed time is 13 seconds, 13.77. So let's make that entry. So 13.77. We have average response time of 1.26, and total throughput of 435 requests per second. Now let's compare these two. For Spring Web application to serve our customers, it took 30 seconds. And on average, every request was returned in 3 seconds. But for Webflux application, it took us only 13 seconds. So within 13 seconds, we served all the 600 customers. And on average, our response time was 1.2 seconds. So you see, there is a huge difference. So we have 3 seconds on average and 1.26 on average across all the requests. So there is a huge gain when using Webflux. And the throughput is 435, and throughput in this case is 195. So in this case, again, the Webflux is performing really well. So let's mark it as green. Now let's move on to the third test, which is 1000 concurrent users. Let's change the port to 8090, and let's change it to 1000. One thing that I forgot to mention is, let me actually save this. So by default, Siege doesn't allow such a huge concurrency. I think the limit is 256 by default, but we can override or change that limit. So it's in a config file on Linux and Macs. It's under home directory and the directory name is Siege and siege.conf. Search for limit and yes, so default is 255. I have just done it to very high number, 10,000. So you'll need to increase this limit to continue with the tests. Now let's get back and let's start the 1000 concurrent user test on 8090. So this is the Spring Web application. All right, so the test has completed. So in total, we have 10,000 requests that we have hit and total elapsed time is 50.84. Let's make an entry here, 50 seconds. The average response time is 4.83. So 4.83. And the transaction rate is 196.70. So 196. So let's just have 196. Now let's run the same test for our Webflux application. So all I need to do is change the port here and let's start the test. All right, so the test has completed. So we have hit 10,000 requests. The elapsed time is only 17 seconds. So let's make this entry. 17 seconds. So average response time is 1.51 seconds and transaction is 587. 587. Now comparing these two results, Spring Web took 50 seconds to address or serve all our 1000 customers. Webflux took only 17 seconds. An average response time of Spring Web application was 4.83. So let's say 5 seconds. So on average, each request returned in 5 seconds, almost 5 seconds. For our Webflux, on average, the request was returned in 1.5 seconds. So you see how huge the difference is. And now coming to throughput, so we're still sitting at 190, around 200 throughput. And in this case, we have reached to 587. So comparing the two results, so the throughput for Webflux application is high as compared, and the response time, the average response time is low as compared to Spring Web. So in this case as well, I would mark this test as successful in the favor of Webflux. You can run more tests and experiment with numbers and see how you go. Just one note before we end this, we have this throughput of web applications sitting around close to 200. And the reason for this is because the Tomcat has 200 threads. And that's why the throughput will never go above 200. It might go closer to 200 even more, but it will never go above 200. Another one thing I wanted to highlight is, so if you go to the console where we are running our Docker Compose, you will see a few errors and they are broken pipe. So we have this error in the blocking service. So what this error means is like the server has disconnected the request before completing the whole. So what's interesting in this is that you will not see any of this error for our non-blocking server. So non-blocking server got started here, like this was our last log line, and I'm scrolling down. You don't see any errors for the non-blocking. And also what you can probably do is browse around the dashboard that we have created. So this is the request per second. So this is the throughput we are rendering here. You will see some data. So this green one is the Spring Web application, which is the blocking one. So there is some data missing here. And the reason why this data is missing is, So Prometheus goes to the application to get the data, but application is so busy that it doesn't respond it back. So this missing data is when the application was very busy. But if you select the Webflux, you will notice that you don't see any missing data. That means the application was not as busy to respond back to the monitoring application. Just one thing I just noticed that there is one small change we should probably do is you go to edit and add this operation, add rate, and run the query and save. So this should give you the rates per second. So let's select this. Now let's go to the dashboard view. So this is the request per second. So previously the graph wasn't coming down. That's because I didn't include the rate. So these peaks are the time when we ran the load test. So in conclusion, we have proven that Webflux application performs better than the Springboot web application. So if you have a scenario where in production, your application isn't able to handle the load anymore, then it would be a good option to change it from the Springboot web to Webflux. That's all I wanted to discuss in this video. If you like the video, hit the like button and subscribe it for upcoming videos. And do let me know in the comments if you have learned something new today. Thank you so much. Until next time.